Hello everyone. So this is lecture 2 for the course Computer Organization and Architecture from the module 1. In today's lecture I am going to talk about the concept of the program and the instruction. What is program and what is the instruction, and then the internal structure of the central processing unit or your processor. What is the requirement from the processor to execute your program or execute your instruction, and the instruction execution cycle I will talk about. So, let us start with a simple program. This program is for adding two numbers. Here numbers are assumed that they are stored in the memory. A and B are the memory locations. So, the first instruction or the first statement which is written here says that the value of A represents here a symbolic name to the memory location, is loaded in the processor register. Let us say register name is R1. So, here A is a source and R1 is a destination. Then again the second load instruction, the memory location, the contents of memory location B are loaded into the register R2. Now, these two values or the numbers are readily available in the processor registers R1 and R2. Now, these R1 and R2 or the contents of R1 and R2 is to be added by the arithmetic and logical unit that is responsible for doing all the arithmetic and logical operations. So, this is an arithmetic operation, adding the contents of R1 and R2 and putting into a new register called as a R3. And finally, the result, the computed result or the addition of the contents of R1 and R2, which are nothing but the value of memory location A and memory location B, is put into the new memory location, let us say C. So, that for that the store instruction is used. So, here two load instructions are used, load R1 comma A, load R2 comma B. So, the values from two memory locations are loaded into the respective registers R1 and R2, and the contents of these two registers are supplied to the arithmetic and logical unit, and arithmetic and logical unit perform the ALU operation, that addition operation, and finally the result is stored into the memory location C. This is a simple program adding the contents of two memory locations. Assume that these two data represented by A and B are represented by the memory location A and B are already available in the memory. So, that is why I am able to load it in the processor and do the operation and store the result. So, this is one simple program. So, from this program we understood that program is basically a sequence of steps, and here in this program how many instructions are there? Load, let us say one load instruction, that is loading one number which is to be added, and the second number two load instruction, one arithmetic instruction I say or computational instruction, and one finally store instruction. Total 4 instructions are there or statements are there. So, if I define what is exactly a computer program. So, computer program is basically a logical group of instructions or statements, usually in high level language like C or C++ or Java. We call these steps as the statements, program statements, okay, and at the assembly level, assembly language level, we call as instructions. That is the only difference. Okay. So, it is a logical group of instructions or statements to achieve some specific task. So it's a logical group of instruction. It is not any kind of group of instruction. Means the any combination of some say load, store, add, subtract, and cannot be a program. It should be a logical. So there is a specific task is there. That task has to perform. To perform that task, we need to write the instructions or the statements in a particular language, computer language that computer can understand in a some sequence. And the sequence is same whatever if I have to solve by hand, in that case also I will follow the same sequence of steps. Definitely to add two numbers, first I will load the numbers, or I will take the numbers, number A and number B, and then I will perform the addition operation on these two numbers. That's definitely third step. Means I cannot do first addition and then reading the number or taking the number. So definitely I have to take first two numbers and then have to perform the required operation, and finally the result has to be either displayed on the monitor or is to be stored in the memory, depends upon the requirement. The corresponding statement has to be right, or corresponding task has to be complete. So now what is the instruction then? Is the instruction a atomic step? Let us say load R1 comma A is a one atomic step or one atomic task? No. It also include a sequence of steps. So instruction is also a sequence of steps. So what are the sequence of steps? Let us say for example in the load R1 comma A. I am writing here load R1 comma A. What are the steps? So load means it has to be read from the memory, that is called as a load. So memory read signal has to be enabled. Before that, memory to memory module you have to pass the information of address from where it has to be read. So here address is represented by A. Then memory read operation has to be initiated, and through the system bus the value stored at the location A will be moved from that location to the register, processor register. Now which register? R1 register here. So R1 registers write signal has to be enabled now. So enabling write signal, control signal for the register R1, enabling memory read signal, and then transfer means through the bus the transfer. So bus has to be acquired and all. So these are the small steps has to be performed to execute this single instruction. And most important, before executing this instruction or start the execution of this instruction, means operation like moving the data from the memory location, one memory location to one of the register in the processor. That's the operation we are doing in this instruction. Before that, what we need to fetch this instruction in the processor, so the processor can understand exactly what is the next step has to be do. So fetching from the instruction, and then the instructions post mortem has to be done according to the information specified in the instruction. So we will see that what exactly how the instruction is represented later in this lecture. So first here we are trying to understand that instruction is not an atomic task or not a single task. In instruction also there are the multiple steps are involved. So my program is a group of instruction, logical group of instruction, and an instruction is also a sequence of steps. To execute any instruction, I need some sequence of steps to be execute, or sequence step has to be performed. So for each step in execution of the instruction, and is an arithmetic or logical operation. Say for example, R3 equals to R1 plus R2. It is an arithmetic instruction. This instruction is reading two values or two register values and putting into the third register. And each step in the instruction can be a data movement, moving the data from, let us say, memory to the processor register, or the processor register to a memory. So in the each step of the instruction, either we are doing some arithmetic logical operation, some computational part, in that the arithmetic and logic unit is involved, or the data movement, we are moving the data from one place to another place, or one component of our computer system to another component, say from processor to memory or memory to processor. And that also is not a single operation, I am saying that. It also involves the multiple small operations, I can say is a micro operations. Enabling the memory is a one micro operation. Memory read, enabling the memory read is a one micro operation. Enabling the register write, so that register can load some new value. So for that the write signal has to be enabled. So that is also a one operation or micro operation. Who perform all these operations? Who do initiate these operations? Control unit. Control units have the overall control on what has to be transferred from which location to which location, and when the appropriate signal has to be enabled such that that particular task or the operation or the micro operation can be completed. So the control unit is responsible for all. So as I said, for each operation one or more control signals has to be activated or enabled. So now to do all these, let us say I have to execute this program which I mentioned in the second slide or first slide, adding two numbers are there in the memory. What I need from the central processing unit or my processor should have what capabilities or functionalities it should be able to do such that it can execute that program. So first is, it should be, or the processor should be able to fetch the instructions. So fetching the instruction means reading the instruction from the memory where all these instructions are stored in memory, main memory. So from main memory these instructions has to be fetched one by one. So fetch instruction is one of the functionality which is required from the central processing unit. That's one requirement. Second requirement is then it should be able to interpret the instructions. Interpretation of the instruction means, now let us say my instruction is load R1 comma A. Now how the processor know that, okay, this means that a memory location A has to be read from the memory and the contents of that location is to be put into the register R1. For a human being, load R1 comma A, okay, is understandable, but how the computer will understand or your hardware will understand? Definitely this information has to be represent, or my instruction is definitely in the form of a binary bits 0101, and some certain codes are there, fixed codes are there for a particular architecture. Every architecture having its own set of codes for these, to identify these operations, load or store or add or subtract and so on. So this complete information, including the register number, what operation has to be performed, how to identify the operand in the instruction or the source location, destination location, what is source, what is destination, what operation has to be performed, all these information is to be there in the instruction. So let's here assume these all instructions are, all these information is there, and now the processor's responsibility to interpret this instruction, identify the operation, and after identifying the operation, it has to initiate this operation to be for the completion. So after interpreting the instruction, let us say doing interpret instruction, I can call as doing the post-mortem of this instruction. Then the third step is fetch the data, because for doing some operation, let us say it is arithmetic operation, means it has to fetch the data. After identifying, okay, this is, they say for example, this is a, let us say it is a load instruction. Load instruction means it has to take the data from the given memory location. So fetching the data, after fetching the data, then if required, some instruction may be required, let us say for R3 equals to R1 plus R2, in this instruction the data has to be processed as well. Okay. So processing means here it involves a addition operation. So in ALU, the adder circuit has to be enabled at that time by the control unit by sending the appropriate control signals or enabling the appropriate control signal, and then the data will be processed. Processing data does not mean always that, okay, doing some arithmetic operation only, it can be a logical operation, also can be a processing. Then finally, if required, some instructions may be required that the data has to be write to the some location, either may be register or maybe in some memory location. So from my CPU I require all these capabilities or functionalities. It should be able to do all these things, then only I can execute my program or execute my instructions. So to do all these tasks, what processor needs now? At the time of designing the processor, then I have to keep in my mind that, okay, I want these things to be done by the processor, then to do all these things what I need. So definitely temporary storage is the first thing which I require. To R1, R2, R3, all these are temporary storage registers used for the temporary storage. Temporary data can be stored and it can be given to the appropriate unit in the processor, and then the further processing can be done. So the temporary storage in terms of register, that is a one thing. Second is the interconnection structure between the various components of the processor. What are the various components? Set of registers. Number of registers vary from architecture to architecture, but in general there are two groups of registers are there. One is called as a general purpose registers and other is a some specific registers. Specific registers, they have some specific meaning, or they can be used for storing some particular information only, cannot be used for storing a general information or general data. So register is a one thing, one component, then arithmetic logic unit is a one component, and then memory and IO. So we need interconnection between the internal components of the processor as well as outside, because if the processor is not connected to the memory module or input output module, then how the data will be transferred from memory to processor and vice versa. So my processor should have the capability of temporary storage, interconnecting all the components inside the processor as well as the outside the processor. And finally the ALU. ALU also required for doing the arithmetic and logical operation. Now we look at the, so let us say we design this processor, a hypothetical processor is designed, and trying to show how it connects or interconnects with the rest of the system module, other modules, memory and the IO module. So let us see what are the things I require or I put in this processor. So here you can see in the processor or a central processing unit called as a CPU, I have some registers, some names are given of the register. I will take one by one, and the IO module is there, means all the IO devices you can say, and the main memory is there. Here is the main memory. So, and this is a system bus which connects all three major components of your computer system. One is a processor, another is a IO module, and third is a main memory. And all these are connected with the help of this system bus. System bus is nothing but it's a set of wires which helps to transfer the data or information from one component to another component. So now let me write first what is PC here. So PC is stand for program counter. This is a specific register or special purpose register, not a general purpose register. The purpose of this program counter, as name specifies, it keeps the address of the instruction which is to be executed next. So from here processor comes to know that okay, this is the place from where the next instruction has to be fetched, and after executing each instruction this PC value has to be updated. Then only the processor can execute one by one instruction from your program which is already loaded in the memory. And here is the memory. So I will take memory later. First let me complete the registers description of my processor. After PC, another register is IR. It's called as an instruction register. Instruction register. Once the instruction is fetched from the memory, it will be put in the register which is called as a IR, instruction register. Instruction is after fetching the instruction is available in IR register. Then third register is MAR. MAR stands for memory address register. Memory address register. Memory address register is used to keep the address of the location from where data has to be read, data or instruction whatever. So let us say for example some location X, some data has to be read. First this value X will put into the MAR and that will be supplied to the system bus, and then the respective module will recognize this address, and if the data is available it will supply that data via the data bus of the system bus. In system bus we have the two set of lines, I can say. One says that carries the data, other is that carries the address. Address lines are used to recognize a location for a particular module. Module can be a memory module or it can be a IO module. Then MBR, next register is MBR. MBR stands for memory buffer register. Memory buffer register. The data, the address which is stored in MAR, and then the contents of that location specified by MAR is read by the appropriate module, and then the contents of that location after reading is put into the MBR is a buffer register. So let us say from X location, so let us say X location data is stored is Y, so Y will be put into the MBR. So this is reading the data which is read from any module, memory or the IO module will be put into the MBR, and address is specified in the MAR register. PC contains the address of the next instruction is to be execute. IR contains the instruction itself. Execution unit is nothing but ALU. It's a combination of circuits like complementer, shifter, left shift, right shift, adder, half adder, full adder, and so on. Okay. Then two registers are there, IO-AR and IO-BR. IO stands for input output, AR stands for address register. The purpose of this register is same as the MAR register, but it is used for the reading input output device or module. Similarly, IO-BR used for the purpose is same as MBR. MBR is used for the memory, main memory, and BR is used for the IO-BR is used for the IO module. Now, what exactly these registers? These registers are the storage, means they can store some number of bits. And what is, how the bit is represented, how the one bit is stored in the computer? The flip-flop. One flip-flop can store one bit. So let us say my size of the PC is, say, let us say 16 bits, means it can store 16 bits. So PC is a, you can say, is constructed by or with the combination of 16 flip-flops. So for 16 flip-flops are used, FFs, to make the 16-bit register, and each flip-flop here is able to store a 1-bit information. And what is flip-flop? Let us say flip-flop is a combination of transistors. So ultimately at the lowest level, on a chip, on a silicon chip, everything are in the form of a transistors. Now some of these transistors are used to design the logic of the computer, and some of the transistors are used to design the memory. Okay. So like that, each register have its own size in terms of that how many bits it can store. Now the question is, okay, so let's, before that going to the relationship between the size and what is the, how the size is decided, let me explain something about this memory. What is memory? Memory is an array of bits. Here also the memory is represented with the help of again the flip-flops, storing each bit. So let us say it can store 10 bits, so the 10 flip-flops are there. So memory is essentially a sequence of locations. Here it is, you can see the location 0, location 1, location 2, and so on. And each location is capable to store some finite number of bits. So it's basically it's a matrix, it's a row and column. Each column is able to store 1 bit, and each row have some number of bits it can store. In the memory, here some of the memory locations have the instructions are stored, some of the memory locations from here to here the data is stored. At the lowest level, there is no difference between the instruction and data, because everything has to be represented by the binary bits 10 10 only. At higher level, this interpretation is there that okay, this is the instruction and this is the data through the program. Okay. So the memory contains data as well as the instruction both. Now memory have the two characteristics. One is which is called as a addressability, or first let us say address space. Address space. Okay, so now I am talking about the memory. One is address space. Address space means the number of locations. how many locations are there. Second term is addressability. Addressability means number of bits at each location. So, let us say the address space is, I have total address space is 2 raised to the power n. Usually it is represented in the, because it is represented in the 2 raised to the power. So, let us say 2 raised to the power n is the total address space, means total number of locations are there. N can be 1, 2, 3, 4, any number, any integer number. Now, to uniquely identify each location, that is required, because the data is stored as per the specified location. So, I need to identify, or processor needs to identify each location uniquely. So, for that I need the address. So, let us say its address space is 2 raised to the power n, then what is the size of the address, or what is the minimum size of the address of each location, such that I can uniquely identify each location, I can give the name. So, let us take a simple example first. Let us say total I have 4 locations in my memory. So, 4 locations means how many bits I require to identify each location uniquely, because the total 4 locations are there. So, let us say first location I can represent with 0 0, second location I can represent with 0 1, third location I can represent with 1 0, and fourth location I can represent with 1 1. So, to identify 4 location uniquely, I require 2 bits or 2 bit address for each location. So, for a address space of 2 power n, I require minimum n bits to identify each location. So, let me write here address bits required for 2 raised to the power n location are n bits. Total n bits I require. Now, come to the addressability. Addressability means how many bits are there at each location. So, let us say m bits are there at each location. Now, what is the total size of the memory? So, size of the memory, how many locations are there? 2 raised to the power n locations are there. 2 raised to the power n locations, and each location contains m bits. Or this is a total size of the memory, size in bits. Now, you can convert into bytes or kilobytes or megabytes and gigabytes and so on. Now, the next question is how these values or the size of these registers PC, IR, MAR and MBR are decided for a particular computer, or in other way, is there any relationship between the memory size or the memory and these register size? So, answer is certainly yes. So, how they are related, we will see that. So, now you know that what PC contains? The address of the next instruction is to be execute. So, PC contains the address. So, address means what will be the size of the PC for the memory, total memory, let us say total memory space is 2 raised to the power n. This is a total memory space, and I want to know the size of the PC, program counter size, and I also know that PC contains the address of memory location, some memory location, because my instructions are stored in the memory. So PC contains the address of the memory, and I know that the memory have 2 raised to the power n total locations. So what is the size of the PC? Means size of the PC should be n, or it is equal to the number of bits required to address the memory location, because I have to specify any of the memory location, because my instruction can be stored at any location in the memory of address space 2 raised to the power n. So that is why I need at least n bits in the PC, so I can identify, or I can distinguish, I can identify, let us say, the memory location. So size of the PC is equals to the number of address bits in the memory. So in this case, if the 2 power n is there, then PC size is n bits. Similarly for MAR also contains the address of the memory, So MAR size is also equals to n bits only. It also contains the address. So the number of bits required for address a memory location, these many bits we should be able to store in the MAR as well. Now IR is instruction register, means the content of memory location are stored in the IR. So I should write contents of memory location, some memory location, any memory location content can be, because my instruction can be stored, let us say this is the location number 3, 0, 1, 2, 3, this is location number 3, and this is the instruction has to be fetch. So my PC should contains 3, so and then that 3 has to be moved to the MAR. So then this 3 information will go to the system bus, and from system bus this memory location 3 will be identified by the main memory module, and then the contents of this instruction, some 1010 information is stored, that will be loaded into via the again system bus only, the data line part of the system bus, and it will go into MBR. Sorry, it will go to the, not MBR, it will go to the IR. Means the size of the IR should be equal to the addressability of the memory. So let us say addressability of the memory is m bits, so IR is equal to the addressability of the memory, what each location contains. Here my assumption is that one instruction can be stored in the memory at one location, or one instruction consume only one location in the memory. Instruction is not longer than one memory location, size of the one memory location. So that is assumption. It may be possible that one instruction can be stored in 2 locations as well. In that case IR should be of that size. But to make it simple, let us say at each location one instruction occupies one location in the memory. In that case the IR size is equal to the addressability of the memory. I should write addressability, ADDRESSBLITY. Okay, so this is addressability of the memory. MBR again, MBR means we are storing the data, so data also occupies the one memory location. So the addressability of the memory in the case of one data can be stored in one location, occupies in one location of the memory, then MBR size is also equals to the m. So here let us say addressability is m, so I can write IR size should be m bits. Similarly MBR size is also m bits. And the same thing will applicable to the IOAR and IOBR. Like the main memory module is there, address space, main memory have the address space, similarly IO module also have the address space. In IO mechanism we will see that this IO module or IO address space can be a part of the main memory, or it can be a separate address space. So that is again a design question. So here right now, as per the picture shows, the IO module is a separate address space. So similarly, the memory locations or the data or instructions are stored at each memory location. Here also a address space is there, a kind of memory is there, where the each IO module or each IO device related informations are stored or buffers are stored, how the data will be, the data which is read from the physically from the device, that will be stored in the buffer, corresponding buffer of that device, and from that buffer the processor can read it. Okay. So each device have the buffers, and these buffers or each device is identified with a, and again with a unique address. So let us say I have 16 devices are there. To identify the 16 devices, and let us say each device will requires one buffer. So for 16 I need how many bits to uniquely identify these 16 devices. So how to calculate this thing? 16 total devices are there, and I have to uniquely identify these devices, how many bits I require, that is the question. So you represent this 16 in 2 raised to the power some n. So here n equals to 4, 16. Let us say 18 devices are there, then I need 5 bits. 2 raised to the power 5 is 32 and 2 raised to the power 4 is 16. So 18 comes in between 16 and 32. So minimum bits I require, that is 5. 4 is not sufficient, because with the help of 4 I can represent only the 16 combinations, and here I require at least 18 combinations. So that is why minimum 5 bits are required in case of 18. Okay. So we understood so far the internal processor structure. So in internal structure you can see here I showed only the registers, the register which required to execute program. We have seen that okay, instruction has to be fetched, instruction has to be decoded, or in the instruction has to be stored somewhere, so the interpretation of the instruction can be done, and then some other registers like the data has to be read, and then some memory location has to be read. For that, what are the additional things we required in the processor? So accordingly we design our processor. Internal connection here has not been shown. So to see that, so this you can see the internal to the processor, the picture inside the processor. So if you want to see the complete picture here, this is inside the processor, and outside here what you have, let us say one system bus is there, and with the system bus let us say IO modules are there, IO devices. Okay, I am representing with a single box, and here let us say you have the main memory, and the main memory is connect via the system bus, it is connected to the processor, and processor internally processor also have the bus or internal CPU bus which connects the components inside the processor. Okay. So let us say this instruction is there, load, or some registers I can specify here. Let us say here the general purpose registers are, that is also part of the processor only. So this is called as a register file. I say this is R1 register, this is R2, this is R3, R4, and so on. So let us say load R1 comma some memory location A, that instruction has to be executed. So let us see that instruction is not an atomic single operation, it involves the multiple operation, sequence of operations are there even in a execution of the single instruction. So let us say after fetching the instruction, when the instruction is available in the IR instruction register, okay, now it will interpret, okay, for the interpretation a separate circuit is there that will identify the individual bits and it will identify okay what operation is there and what is the source. Let us say operation is load. So load operation means from where to where data has to be moved. So from main memory to one of the register which is specified in the instruction, the data has to be moved. So, first the memory read operation has to be initiated. So, read operation, the address of that location will be passed into the MAR via these buses, and these bubbles are nothing but, which is, you can say, they are working as in a gate, like a switch. So, if it is closed, then means information can be passed. If it is off or it is open, then the information cannot be passed. Okay. So that address which is reached, the A location address will be there in MAR, and MAR use that information, the contents of MAR will pass to the system bus. This is the main bus of your system or your computer, called as a system bus, and from there the memory contents will be read, and after reading these contents it will be put into the MBR. So, now the contents of memory location A are available in MBR, and then from MBR it will be stored in the register IR. So, from MBR it will go via this bus and go to this R1 register. So, even for executing this single instruction also, there are multiple steps are there. This is the way how inside the processor instruction execute. So, as we seen that instruction is not an atomic single step, it is a multiple sequence of step is required even executing a single instruction. So, what are the steps? Now, how to see that? So, steps are, let us say I divide first in a very simple way 2 steps. One is a fetch, one is a execute. Fetch means fetch the instruction, put into the IR, and after that rest of the things are included, or I am calling as an execute. So, through this diagram you can see there is a fetch cycle is there, that is responsible for fetching the instruction one by one as per the information available in the program counter, and next is execute cycle that do the rest of the thing. So, what is fetch cycle? The program counter holds the address of the next instruction is to fetch. So, processor know once your program is loaded into the memory, the place where the location where the first instruction is loaded or your program start loading, means the location first, that address is stored in the program counter, and from where the processor knows that this is the location from where the instruction fetching has to be start. Then after fetching the instruction, next is to fetch the next instruction, the PC value has to be incremented such that now it indicates the next instruction, address of the next instruction. So, PC value will be incremented. So, let us say each location contains one instruction, or one instruction occupies one location in the memory. In that case, PC value has to be incremented by 1, PC plus 1, PC equals to PC plus 1. Okay. And this increment PC is applicable in the sequential execution of the program, means the one by one instruction in a sequence has to be executed from your program. Sometime it may be possible that okay, your program is not executing sequence in a sequence. You might have wrote some C program in that you wrote a if statement or a for loop statement. In that, what will be the next instruction will execute? For example, in case of a if, it depends upon the condition which you wrote. If the condition is true, then the next sequential instruction will execute, otherwise condition is false, then it will go to the else part. So, it will execute not exactly the same next instruction in the sequence, it will be somewhere far from the next sequential instruction. So, it breaks the sequence. So, in that case, so that is why here it is written that unless it is not told otherwise, means some jump instruction, that is the notion of the jump instruction. So, if condition is true, do this, otherwise condition is false, then do this. So, in that case always PC is not like that, it is incremented by 1 or incremented such that it represents the next sequential instruction only. This PC value can be modified through the logical sequence of the program as well, with the help of some conditional instructions. Then after fetching the instruction is to be loaded in the instruction register, that is called IR, instruction register. Now processor interprets this instruction, and that interpretation is called as a decoding the instruction and perform the required actions further. So this is a fetch sequence. Now come to the execute sequence or execute cycle. So in execute cycle, let us say after interpretation of the instruction, finding that what operation is there and what are the operands from where it has to be taken, after identifying all these things, then it will start the processing that comes under the execution. So in execution, one thing is maybe the data transfer, let us say load instruction is there, load R1 comma A. So moving the data from memory to the processor register. So that is a one way of or one type of instruction, that one type of, you can say, the processing in which the data movement is there from processor to memory, or it can be a memory to processor as well, or it can be IO module, it transfer between the data transfer between the IO module and the processor. For some instructions, maybe you required some arithmetic and logical operation on the data, say for example R3 equals to R1 plus R2 from our first program. In the processing, it may be the alteration of the sequence of operations. For example, in a jump instruction, I gave the example for high level language instructions like if or conditional statements and the looping statements. So the alteration of the sequence of operation also a part of execution, or it can be a combination of maybe the data transfer plus the alteration as well, or some arithmetic operation as well as the alteration or the data transfer. Now the big question, so far I explained that okay, instruction is there, and okay, instruction is represented in the form of binary because the machine hardware, your hardware can understand only the 1010 form of that. It is a transistor, so transistor can be on and off, either on or off. So the on state, let us say, represented by 1 and off state is represented by 0. So everything is stored in the form of 1010. As a human being, let us say for example I wrote instruction like load R1 comma A, but the computer cannot understand exactly load. This load has to be encoded in the binary information. So the instruction is also represented in the binary. So let us take example, what exactly instruction, what are the parts of the instruction and how it is represented inside the computer. So as I said, the instruction is nothing but a sequence of bits. Major two components are there, one is called as opcode, another is called as a address bits. So here opcode bits you can say, address bits, or you can say operand as well. For any instruction, exactly instruction is what? In instruction, two informations are important. One is what operation has to be performed, and once you know the operation, then the next thing is that where the operands are there on which this operation has to be performed, and after performing the operation, what has to be done? Result, where the result has to be stored. This is your instruction in general also. Suppose somebody says that okay, you have to add two numbers, you will say first ask that where the two numbers are there. So we will get the numbers first. So first what you came to know? You came to know that okay, addition has to be performed. So addition means you know that okay, there are two numbers are required to add, and after getting these two, after knowing that okay, this add operation, and then add operation can be done on two numbers, so you require two numbers. So what is the where these two numbers are available, that next information you require. And once you know these two numbers, then the place where these numbers are stored, you have to read the numbers from there and then perform the operation, and finally you require that where this result has to be stored. So you will, so this information you require even you are doing without computer as well. So in case of the computer, okay, this is not the third part, it's a slash, so address bits or the operand. So here also opcode bits means it tells about the operation. So let's say one architecture supports some 20 operations or 20 instruction, different instructions. So for 20 instructions, how many bits I require for the to identify individual operation uniquely. So 20 I have to represent, let's say 2 raised to the power 4, that will become 16, 2 raised to the power 5, that will becomes 32, 20 comes in between that. So let's say minimum 5 bits. So how many combinations of 5 bits? Total 32 combinations, out of 16 will be used, or maybe rest of the later on can be added. Right now maybe. So my opcodes will be like that, 5 bit. So starting from 000, 50002, 001, 00010, 00011, and so on. Total 32 combinations will be there. Out of the 16 can be. So minimum 5 bits I require for opcode. So say for example 000 means in some architecture it's a add, and 0001 means it's a subtract, and so on. Then the rest of the part of the instruction, that again also represented in the form of the binary digits. The rest of the part also, that tells me, let's say add, so opcode bits are 5 zeros are there, then this rest of the part it needs to tell me that where the 2 operands are there on which this add operation has to perform, and what are the address of. If they are available in the register, the register address will be there. If these 2 numbers are directly available in the instruction itself, then instruction, then these 2 numbers will be read from the instruction only. Or if these 2 numbers, one is available in the register, other is available in the memory, so all possibilities are there. These 2 numbers can be in instruction, can be in registers, one can be in register, one can be in memory, both can be in memory. So this is something is called as the addressing modes, means where the operands are there, how operand is represented in the instruction. So definitely some bits I require in the instruction that tells me exactly where the operands are there. Registers, then the rest of the bits has to be interpreted such that, okay, it is giving me the address of the 2 registers from where the data has to be read, and that data I have to use for the doing the add operation. Okay. So to understand this, so here we just try to understand that what is my instruction contains. Instruction is a sequence of bits. Some bits of the instructions are represent the operation code, which operation has to be performed, and the rest of the bits tells about the operand and the storage about storage about the result, where the result has to be stored. Okay, let's take one example to understand this execution of this program execution on the hypothetical processor which I showed you in the previous 2 slides. So to understand this, so here these are the opcodes I am using. 0001 means load. AC is accumulator register, it's again one specific register or special purpose register called as accumulator. So the date, if you are using load instruction, you say load AC means the data from the memory location specified in the load instruction, and where the data will be put, say simply if you will say load A. So here source is given that, okay, from this memory location A memory location data has to be read, but destination is not given. So the destination is implied here, says everything will go in the, if you are taking reading from the memory, it will go to the, your destination is always fixed, that is accumulator register. So no need to specify in the instruction, it will save the number of bits in your instruction. So it's implied that the whatever you are loading from the memory, it will go to the accumulator register. This is always fixed, it is hard binded in your hardware. Similarly, for store, if you say store B, you say store B means it will store in the memory location B, but what it will store? The contents of accumulator. So here source is fixed. So this is the way how my processor is, internal processor structure is there. So there one opcode says that 0001 4-bit opcode is there. The load AC, contents of AC from the memory, load AC from memory, and 0010 store the AC to the memory, and 0101 add the contents of AC to memory location, and finally result will be stored in the accumulator or AC register. So in hexadecimal, I can represent this as a 1 decimal or hexadecimal, and it is 2 and it is 5. So here you can see this is my memory, and memory is here the numbers, the memory addresses are shown in hexadecimal digits. So each hexadecimal digit represent 4 binary bits. So if I want to write 300, so 300 will be written in binary, 3 will be represented by the 4 bits 0011, and then 0 will be represented by 4 bits, and then this again 10 will be represented 4 bits. So it's a 12-bit address total. So the total address space you can say for the memory is 2 power 12, and 12 bits requires to represent a individual memory location. So these numbers are shown in the hexadecimal. So now this memory, each memory location contains what? 4 hexadecimal digits. So in a binary it will be 16. So the addressability of this memory is 16 bits. And how to represent one? How to represent 1 in a binary? 0001. So you can say this 0001, and 9 will be 1001, 4 will be 0100, and the 0 will be 000. Okay. So like that. So now what PC contains? 300, the address of this memory location. So the contents of 300 memory location 1940 will be loaded into the IR. 1940 here you can see in IR, and the PC value is incremented by 1. So you can see the PC value is 301. Now 1940, what is 1940? This is instruction. So first 4 bit of this instruction is 1. 1 means opcode is 0001 represented in binary. So what is this instruction means? This meaning of this instruction that is already defined in the architecture is memory location. Which is memory location? The rest of the part shows the memory location. So 940 is a 12-bit. This is a memory location. So contents of memory location 940 will be loaded in the accumulator register. That is the meaning of this instruction. So you can see here contents of memory location 940. This is a 940 memory location. What are the contents? 00003. So 3 will be loaded into the accumulator here, and the PC is incremented by 1. Now PC is 301. Now at 301 memory location will be read, and that instruction which is stored at 301 that will be loaded into the IR. So now IR contains 5941. So this is the instruction. So here the interpretation has to be done. So first 4 bit of this instruction, that is 5 in hexadecimal. So 5 is 0101. This 5 has to be. So what is the meaning of the 5 in this architecture? It says that add to AC from memory. From memory, what is the memory location? 941 is the memory location. The rest of the instruction part shows the memory location. So 941, what is stored at the 941? 2. So this 2 value has to be loaded into that has to be added. This 2 value is to be fetched, and that has to be added to the current contents of AC. Current contents of AC is 3. So 3 plus 2 equals to 5, and finally AC will be loaded with the result of this addition. That is the meaning of this 0101 opcode or operation code. Then in the meantime PC value is incremented by 1. So now PC indicate to the memory location 302, and 302 what is stored? 2941. Now 2941 will be loaded into the instruction register, and here 2 is a operation code. What is operation code? 0010 in the binary. So 0010 means here you can see store AC, store the contents of AC into the memory. And which memory? Memory location is 941. So 941 memory location is loaded by the current contents of the AC. AC current contents are addition of the 2 plus 3. So that is loaded into 5, and this stops the program here. So this is the way how a program will is execute instruction by instruction in a sequence. So now look at the instruction cycle diagram. Right from fetching from the instruction, fetch the instruction, and then interpreting the instruction or decoding the instruction means identifying the opcode and the operands or address of the operands, and then after identifying, then these operands has to be fetched. If multiple operands are there, then the multiple operands has to be fetched. So here you can see first is instruction address calculation is there. Calculate the instruction address where it is available in PC. Then instruction has to be fetched. The next stage is fetching the instruction. After fetching the instruction has to be decoded or interpret whatever. So here I am calling as in a decode the instruction. And after decoding the instruction, then you will come to know that what operation has to be performed and where the operands are there, or how many operands are there. So it will do the operand address calculation from the rest part of the instruction, whether the operand is in registers or operand is in a memory or operand given in the instruction itself. In the previous example, we have seen that operand is available in the memory, and the remaining 12 bits of the instruction are telling the address of that memory location. So in that case, the operand address calculation is there, and then fetch the operands. One operand is there, fetch one operand. The multiple operands are there. In some instruction maybe require multiple operands. So fetching the multiple operands. And after fetching the operands, now you know the operation, you know the operands, you fetch the operands, now everything is available. Now do the operation which is identified during the decode phase. Okay. So the data operation will be performed. After performing the data operation, then the destination operand address calculation is to be required, where the result has to be stored, and then store the operand. If the multiple operands are there, say for example you are doing operation on array of a list, in that case the multiple operands has to be stored. And after doing this, your one cycle is over. So for, as I said, that for a string operation on a string or on the vector data or your array of list, it will come again here, again it will calculate the address, operand address, fetch the operand, and then do the operation, and it will store till the complete list is not over. For a single operand instruction, it will store the operand and then go for the next instruction, look at the PC value and then accordingly fetch the next instruction. So this is your instruction cycle diagram. So now we understood that instruction execution also is not a single atomic operation. In this diagram you can see the stage, this stage: instruction fetch, instruction operand, fetch operand, and operand store. These states require memory access. We need to access the memory for executing these states or states. So now after understanding whole these things, we are in a position to answer the following questions. So what are the which of the instruction cycle state require main memory access? So 3 states are there: fetch instruction, fetch operand, and store the data. For these 3 states we need to, or processor need to access the memory, main memory. What is the context switching? And this is third question. The third question is, let's say assume the main memory address space is 2 raised to the power 16. So address space means the number of locations, and each location contains 1 byte of the data or instruction. You can say 1 byte of information is at each location. So addressability is 1 byte or 8 bits. To find out the minimum possible size required for the registers like program counter, memory address register, memory buffer register, and the instruction register. And what is the total size of the memory? Then same question you can repeat for the address space of 2 raised to the power 32. So let me give the answer of this third problem. First part says a PC, the value of what will be the size of the PC. So your address PC contains what? PC contains the address of the instruction is to be execute next. So means PC contains the address, memory address. Now total memory address space is what? 2 raised to the power 16. So what is the how many bits are there in address, memory address? 16 bits are there. So PC value should be 16 because PC contains the address and address bits are 16. So the minimum number of bits required for the PC is 16. And for MAR also contains the address, which data has to be fetched or which memory location has to be accessed. So that information contains the MAR, memory address register. It is called as address register as well. So the address bits are 16, so in that case 16. For MBR and IR, the number of bits required as per the addressability of the memory. So here addressability of the memory is 1 byte. So minimum 8 bits are required. And total size you can calculate. You multiply addressability with the address space, you will find the total size of the memory. So that's all for this lecture. Thank you very much.